For centuries, humanity has looked to the sky, wondering if other worlds exist beyond our own. But now we know that among the surrounding stars, there are planets orbiting them. Some are massive giants, locked close to their stars. Others lie in the shadows, far enough away to remain cold and hidden. And yet, among thousands of discoveries, there are a few worlds close to us, close enough to imagine we could reach them. These nearby planets are not just glowing dots. They are clues, bringing us closer to answers to questions that once seemed impossible. Could any of these worlds harbor life? How similar or alien might they be? The search for exoplanets has transformed from myth to method. Now the question is not whether other worlds exist, but how many there are and what secrets they may hold. Our story begins in 1995 when 51 Pegasi b became the first planet discovered orbiting a star similar to our Sun. A discovery that shook the foundations of astronomy. For centuries we wondered, do other worlds exist beyond our planet? Early science fiction writers imagined distant planets suitable for life, while scientists endlessly speculated. But until this moment, planets outside our solar system existed only in our imagination. The answer, however, was hidden in the silent motion of stars, detectable only through new technology. Swiss astronomers Michael Mayer and Didier Queloz, leading a team equipped with powerful spectrographs, found the first signs of an exoplanet orbiting a sun-like star in the Pegasus constellation. They announced that there was indeed a massive gas giant similar to Jupiter, but orbiting much closer to its host star, completing an orbit at an astounding speed every 4 days. This discovery was made possible by observing a wobble of 51 Pegasi, a tiny but noticeable shift in the star's position caused by the gravitational pull of an unseen companion. The radial velocity method, used here with great success, allowed scientists to measure this minuscule shift in starlight, somewhat like a faint drumbeat in a distant room. It's a subtle vibration we can sense but not see. The radial velocity method enabled scientists to detect this heartbeat of the star, concluding the presence of a planet by analyzing regular oscillations in its spectral data. The discovery wasn't just proof that other planets exist, but proof that we could find them. For the first time, the scientific pursuit of planets outside the solar system stopped being purely speculative and transformed into a tangible search. The discovery shed light on an entirely new field of astronomy, planetology. However, for some of our erudite viewers, a very logical question may arise. Was 51 Pegasi b truly the first observed exoplanet? It's a good question, and the answer is nuanced. Pegasi b was the first confirmed exoplanet found orbiting a sun-like star in 1995. However, it was not the first exoplanet ever observed. In fact, the first confirmed exoplanet was discovered orbiting an entirely different type of object, a pulsar. In 1992, astronomers Alexander Volshan and Dale Frail discovered 2 planets which were given evocative names, Poltergeist and Phobator. However, these planets orbited a rapidly spinning neutron star Lick, named after a powerful fictional undead creature since it made their environment vastly unlike any conceivable planetary system with conditions far too hostile for life as we know it. Thus, Pegasi b received special recognition because it was the first confirmed exoplanet orbiting a sun-like star, suggesting that planets could exist in environments more familiar to us. This discovery sparked a wave of exoplanet research focused on stars that might resemble our solar system. Beyond confirming the existence of exoplanets, the discovery of 51 Pegasi b expanded our understanding of their diversity. How could a gas giant form so close to a star without being engulfed? Until then, many astronomers believed that only small rocky planets like Earth could orbit a star up close. And this hot Jupiter made us rethink models of planetary system formation. Along with it, the search for planets turned from an isolated theory into one of the most dynamic areas of discovery in modern science. A year after the previous discovery, astronomers found another exoplanet, this time around 47 Ursae Majoris, a star located 46 light-years away and surprisingly similar to our Sun, but this discovery was different. While Pegasi b was a hot Jupiter orbiting very close to its star, Ursae Majoris b had an orbit much farther away, with an impressive orbital period of nearly 3 years. In other words, this planet orbits its star at a distance similar to the gas giants in our solar system, making it the first long-period exoplanet found around a main sequence star. This discovery was significant, as it hinted at cosmic order beyond our own system, suggesting that our solar system structure might not be unique. But finding it was no easy task. Unlike close orbiting planets, which can be detected with relatively short-term observations, Ursae Majoris b required meticulous, repeated measurements over a long period. For nearly 9 years, astronomers had to observe the faint wobbles of the host star's light, tracking each tiny shift, every hint pointing to a hidden planet. Yet with each observed light shift, astronomers moved closer to the proof they sought after. This discovery gave way to new hypotheses that planets could form and maintain stable orbits in many types of star systems, expanding the scope of exoplanet studies. Realizing that distant star systems could mimic the arrangement and order we see in our system prompted astronomers to consider the possibility of planet formation in a vast range of conditions, from the outskirts of red dwarfs to the expanses around yellow stars like our own. A couple of years later, in 1998, astronomers discovered Gliese 876b, an exoplanet orbiting a star twice as close to us as any previously discovered, at a distance of just 15 light-years. This wasn't just another distant point of interest. It was a potential neighbor in the infinite cosmos. This discovery added a new level of tangibility to exoplanet research, suggesting that planets exist not only somewhere out there, in an abstract sense, but much closer than we could have imagined. However, this exoplanet also posed a unique challenge. It orbits a red dwarf, a type of star with properties vastly different from our Sun. Red dwarfs are smaller, dimmer, and cooler. And for years, astronomers doubted that these stars could be host to planets, especially large ones. A gas giant orbiting close to a red dwarf once again defied existing theories of planet formation, pushing scientists to rethink and adapt their understanding of where and how planets might form. Initially discovered through the combined efforts of the W.M. Keck and Lick observatories using the radial velocity method, Gliese 876b turned out to be a massive gas giant. Its existence confirmed by observing the faint wobble of its parent star. This back and forth motion, caused by the gravitational pull of its unseen planet, showed that the red dwarf was indeed significantly influenced. To collect precise data on the planet's mass, astronomers employed an astrometric technique using the Hubble Space Telescope, an unprecedented method enabling researchers to receive highly accurate mass measurements. Using Hubble's fine guidance sensors, a specialized instrument typically used for telescope aiming and stabilization, a team led by George Benedict and Barbara MacArthur measured the side-to-side wobble of Gliese 876. Over the course of 2 years, they meticulously mapped this small shift, comparable to the size of a quarter viewed from 3,000 miles away. These measurements revealed that the planet's mass is 2 to 2.5 times greater than Jupiter's, which allowed them to classify it as a low-mass gas giant and the first exoplanet whose mass was confirmed through astrometry. These precise measurements allowed astronomers to confirm that the planet orbits its star at an inclination nearly identical to Earth's, a crucial detail for determining mass accuracy. Hubble's astrometric confirmation marked a significant advancement, establishing a method later used for confirming dozens of other exoplanets. This uncovered a new era of precision in mass and orbit determination. Meanwhile, let's jump to the year 2000, to the discovery of Epsilon Eridani b. It was a milestone that showcased the increasing sophistication of methods used for searching for planets and underscored the need for precision in astronomical measurements. This exoplanet was later given its own name, Aegir, representing the ancient Norse sea god. According to mythology, Aegir is married to the goddess Rain, who also represents the sea. Thus, the star Epsilon Eridani received her name. Aegir is a gas giant with a mass about 80% that of Jupiter, orbiting at a distance of roughly 3.5 astronomical units from its host star. It takes Aegir about 7.6 years to complete one orbit. Detecting it was a challenging endeavor. It took decades worth of data, and the scientific community was highly skeptical due to the complex behavior of the star itself. The early signs of a planet orbiting the star transpired in the early 1990s, led by a Canadian team using Doppler spectroscopy. However, initial observations were too vague to confirm the planet's presence, leaving room for doubt. The magnetic activity of the star complicated the data, creating Doppler noise that made it difficult to isolate the gravitational influence of the planet. Years of collected data and method refinement were required before a team, led by Artie Hatzies, could definitively confirm the existence of Epsilon Eridani b in 2000 using the Doppler shift, a method sensitive enough to detect subtle changes in the star's velocity. In 2006, astronomers took another step forward in regards to confirming the existence of Aegir using astrometry with the Hubble Space Telescope. Under the guidance of George Benedict and Barbara MacArthur, who we met earlier, the team measured the star's minuscule side-to-side wobble. This astrometric technique was sensitive enough to accurately determine the gravitational pull of the planet toward Epsilon Eridani and prove a more precise estimate of its mass. These observations showed that the exoplanet's orbit was inclined nearly edge-on to Earth, meaning the planet's orbital plane around its star almost aligns with our line of sight, which in turn tells us the planet pulls its star directly toward and away from us in a measurable way, making the detection of Doppler shifts in the starlight especially effective. Scientists concluded that Agar's mass is approximately 1.5 times greater than Jupiter's, although later refinements placed it closer to 80% of Jupiter's mass. However, the process was still far from simple. Observations using the Spitzer Space Telescope in 2006 discovered an asteroid belt near the orbit of Epsilon Eridani b, raising concerns about the stability of its orbit. Had the planet's orbit been as eccentric as initially suspected, it would have destabilized or disrupted the asteroid belt. This led scientists to reassess the eccentricity of the orbit. Further studies published between 2019 and 2022 revealed that Agar likely has a nearly circular orbit with an eccentricity close to 0.07, which stabilizes its movement within the asteroid belt. Despite these findings, Epsilon Eridani b remains challenging to observe directly. Attempts to capture its image using the Sphere instrument on the Very Large Telescope in 2019 and 2020 did not confirm observations, even after more than 38 hours of exposure over 12 nights. These difficulties underscore the limitations of existing technology in detecting low-luminosity exoplanets, particularly those orbiting dim stars like this one. Today, with the extended infrared capabilities of the James Webb Space Telescope, astronomers hope to finally obtain a direct image of Agar, which could reveal new details about its atmosphere and composition. The story of this discovery vividly demonstrates the importance of precision, long-term data collection, and continuous technological advancement for understanding exoplanets. The next milestone in exoplanet science was the discovery of Proxima Centauri b in 2016. Orbiting the star closest to our Sun, only 4.25 light-years away, this planet became the closest known exoplanet to us. Proxima Centauri b immediately drew astronomers' attention due to its Earth-like characteristics, a similar mass and an orbit within the habitable zone of its star, a region where temperatures could allow for liquid water. This combo of proximity and potential habitability made its discovery historic, sparking enormous excitement and hope in the scientific community. The discovery was the culmination of marking years of focused long-term observations under the Pale Red Dot Project. Launched specifically to detect an exoplanet around Proxima Centauri, the project represented a substantial collaborative effort with astronomers worldwide meticulously monitoring tiny changes in the star's light. By tracking minuscule Doppler shifts caused by the gravitational pull of the planet, scientists confirmed its existence and some characteristics. The success of the Pale Red Dot Project stands as a testament to the dedication of astronomers who, despite the challenge of detecting such faint signals, remained unwavering in their commitment to finding nearby worlds. These observations took several years and required extremely precise measurements as the star's own flares and activity complicated the data. In the end, the team's hard work paid off, proving that not only did the planet exist, but also the fact that it was close enough for in-depth study, possibly even with direct imaging in the near future. Due to its proximity to Earth and potential habitability, Proxima Centauri b has become a prime candidate for future exploration. The possibility of studying it up close, or even sending an interstellar probe there, has stirred discussions among scientists and engineers worldwide. Projects like the Breakthrough Starshot Initiative propose sending ultralight nanocrafts moving at the speed of light, propelled by powerful laser beams, to reach the system within decades. These probes could capture the first images of the planet, revolutionizing our understanding of exoplanetary environments. In just a few decades, we've gone from the first signs hinting at planets beyond our solar system to a catalog containing hundreds of worlds, each one showcasing the diversity of planets within our galaxy. Every nearby exoplanet we've discovered works toward deepening our understanding of what makes a planet unique and what could make it habitable. As technology advances, we're getting ever closer to direct observations and the tantalizing possibility of exploring these worlds up close. From detecting distant wobbles to imagining interstellar probes, our search has transformed the night sky into a map of possibilities, bringing us closer to understanding our place in the cosmos. Today, exoplanets inspire not only our questions, but our ambitions, pushing us toward a future where discovering our neighbors in space is more than a dream. It's our next frontier. Latest research into solar activity shows that humanity's time on Earth is slowly coming to an end. The behavior of our star has resulted in big changes on Earth several times before, but what if future changes are so significant that our civilization cannot adapt to them? If we had to leave Earth right now, what are our chances of finding a new home? What new planets have been discovered by the scientists, and is there a new Earth among them? Let's find out right now. For starters, let's talk about what it is that we're actually looking for. All of the planets found outside of our solar system are called exoplanets, but not every exoplanet is suitable. For example, there are quite so-called rogue planets. They revolve around the center of the galaxy, not tied to any star. Due to the lack of conditions that only a nearby star could provide, these kinds of planets are not suited for humans. The main problems encountered in the search of exoplanets are the distance, their size in relation to their star system, and light. Unfortunately, unlike stars, very few exoplanets have enough luminance for us to see them in the light of a star that formed their system. Furthermore, the presence of such luminance can indicate certain problems. For example, a planet might be too close to its sun, and therefore too hot. When searching for a new home, we must also account for its location within its own star system. First and foremost, we want to know whether the planet is in the so-called habitable zone. The habitable zone refers to the distance from the star that allows for the existence of water in its liquid form. Additionally, the planet can't be too cold or too hot. A prime example of how hard it can be to spot the kind of planet we're looking for is the famous pale blue dot. A photo of Earth taken by the Voyager probe from the outskirts of the solar system really shows how difficult it is to spot something in space. Fortunately for us, there are several ways to find exoplanets. The most obvious way, direct observation, which involves observing the cosmos using telescopes and probes. But this method faces the issues of distance and luminance. As of right now, only a few planets were discovered via direct observation. For a planet to be discovered via this method, it has to be large and bright. Thanks to such characteristics, the planet 2M1207b, which has the mass equal to 10 Jupiters and surface temperature over 1600 kelvins, became the first exoplanet that could be observed using this method in 2005. The other method of finding exoplanets is the transit method. Most exoplanets were discovered using this method. The gist of this method is basically trying to notice the dimming of starlight over time. So why would their light dim? As the planet orbits around a star, at a certain point, the planet would be positioned between us and the star, blocking some of its light. A good example of that are periodic solar eclipses we're able to observe from Earth. We know that when celestial objects are positioned in a certain way, we can observe the way the sun is fully or partially blocked by a passing planet or the moon. And so when we see a star being dimmer than before, we're observing the transit of its satellite, an exoplanet. The most studied planet found outside of the solar system using this method is Osiris. So hot and large that when it transits the star, it dims its light by 1.7%. It's so hot that it was nicknamed the evaporating planet. It was even found to contain water vapors in its atmosphere. The third most successful method of searching for exoplanets is the Doppler method. It used to be a primary way of finding exoplanets before the transit method. The method essentially uses a spectrometer to observe changes in a star's luminosity. When there is a relatively large object orbiting the star, its movement causes shifts in the star's light spectrum. One of the most fascinating planets discovered using this method is the Kepler 11c, which was found to have an Earth-like atmosphere containing helium and hydrogen. As of today, we know of around 5,200 exoplanets. However, only a small portion of them can be considered candidates for becoming Earth 2.0. There are good reasons for that. The first one is the classification of exoplanets. Let's take a closer look at the different types of exoplanets. We'll start with the largest and most diverse type, gas giants. So far, we've discovered over 1,500 of them, and they're all incredibly large. However, there is something that sets them apart from the gas giant found in our solar system, Jupiter. They are very hot. Normally, gas giants have a solid core surrounded by flowing gas like helium or hydrogen. And while on Jupiter the gases are cool, the gases on the aforementioned planets are so hot that some of them have a higher combustion temperature than that of our Sun. It goes without saying that these planets are not appropriate for habitation. Another type of exoplanets, just as prolific as gas giants, are Neptunian exoplanets. There are over 1,700 of them that we currently know of. These planets are more similar to Earth, both in their high content of metals and the presence of an atmosphere. Although they contain metals and their atmosphere contains hydrogen, helium, and sometimes even oxygen, these planets are usually either too far from the parent star, just like Neptune in our solar system, or too close, which results in them gradually burning out, something we are able to observe on our system's rocky Mars. Among the Neptunian exoplanets, there are two that present the most interest to us. Gliese 436b was discovered in 2007 and is unique due to the fact it is made almost entirely of water. On top of that, the planet's surrounded by hot ice with a temperature around 570 degrees Fahrenheit. It has an atmosphere that mainly consists of helium, and as the planet orbits its parent star, it leaves a huge trail of hydrogen. Gliese 3460b was discovered in 2012. Its atmosphere is also full of helium and hydrogen and is much more dense than Earth's atmosphere. It's possible that at some point of their existence, these planets will eventually have the kind of atmosphere conditions we need, but there's no guarantee that they'll be able to sustain those conditions. For example, Gliese 3470b loses around 50 to 100,000 tons of helium per second. But still, scientists seem to think that some of these warm Neptunian exoplanets are in transition and have the potential to form into an entirely new type of planet, a super-Earth. Super-Earth sounds promising, doesn't it? Well, don't rush to celebrate it. In this case, the prefix super doesn't mean it's better than Earth. It actually just refers to the size of the planet, which is several times larger than Earth, but smaller than the giant of the solar system, Neptune. Significantly fewer planets of this type have been discovered, around 900, but their composition is much more similar to Earth, and the conditions are closer to the kind we need for survival. A few super-Earths come to mind. The nearest super-Earth is Barnard Star B, located only 6 light-years away. However, it doesn't get much light from its parent star. According to the scientists' calculations, it only receives the equivalent of 22% of the energy that Earth gets from the Sun. The next interesting planet is Kepler 22b, an exoplanet 14 times bigger than the Earth, although it's theorized to be entirely covered by ocean, which means there's a chance that there could be life on Kepler 22b, since calculations indicate that the temperatures on this planet range between 12 and 70 degrees Fahrenheit. In July 2017, another super-Earth was discovered. It was named Lytton B. Its most interesting feature is that the amount of energy it gets from its parent star is very close to what we get from our Sun, only 6% more. It's also likely that it's made of rock, and considering its atmosphere, the range of temperatures on this planet are very similar to Earth's. Then very recently, at the start of October 2022, a new exoplanet that was assigned the moniker LP890-9c was discovered. Not only is it in its star's habitable zone, the temperatures on the surface are pretty pleasant. At the moment, it's considered the second most prospective planet of this type for potential human relocation. And although super-Earths make scientists feel moderately optimistic, there's a rare but most prospective type of exoplanet, terrestrial or rocky planets. So far, only around 190 of them have been discovered. It's very likely that there are many more out there, but since their size is so close to Earth's, it's difficult to spot them, unlike gas giants or hot Neptunians. In the solar system, Earth, Mars, Mercury, and Venus are the 4 terrestrial planets. Outside of the solar system, planets ranging between half and twice the size of Earth are considered terrestrial, some of them being even smaller. Exoplanets that are larger than twice the size of Earth are considered super-Earths. The closest and most similar in temperature and composition to Earth are Ross 128b and Gliese 667c. Ross 128b has quite a wide range of temperatures, between -76 and 70 degrees Fahrenheit, which is primarily due to its proximity to its parent star, whereas Gliese 667c has the average surface temperature of 80 degrees Fahrenheit, but it always faces the star with the same side. So it's possible that it already has primitive life forms around its pole, which is close to the star. What method is humanity currently using to study space in search of exoplanets? The most effective tool at this moment among the ones out there in space is the Kepler Space Telescope. Even though its mission was supposed to only include 3.5 years of observing a relatively small part of the sky, it manages to observe over 100,000 star systems simultaneously. 100,000 star systems. Be familiar with the method of finding exoplanets used on the Kepler telescope. It is the search for the presence of planets using the transit method. Remember, the main principle of this method is observing periodic changes in the brightness of stars. Kepler's work resulted in finding over 3,400 exoplanet candidates, more than 1,000 of which were subsequently confirmed as planets by further research. In the end, it worked for over 9 years and ceased to function in 2018. The first 5 hot Jupiters were discovered thanks to the Kepler Space Telescope. A little while later, it detected the smallest known exoplanet, which is only 1.42 the size of Earth. Kepler 10b is the first one of the officially confirmed planets composed of iron. It's a shame that its temperature range exceeds 2,700 to 5,400 degrees Fahrenheit. But the things considered most interesting among its findings are the Earth-like planets Kepler 438b and Kepler 442b, discovered in 2015, both of which are in the habitable zone of their parent stars and considered incredibly promising. Located in the habitable zone of its red dwarf, Kepler 438b still requires detailed study because the flares of its star, which are dozens of times more powerful than those on the Sun, they may cause considerable harm. It's worth mentioning that even though the telescope stopped working in 2018, the data from its observations is still being received and processed. So it is possible that the list of candidates for Earth 2.0 would only expand. To replace the Kepler telescope, the TESS telescope was launched in 2018. Unlike its predecessor, the TESS telescope will primarily explore the space nearby, limiting its search to a distance of 200 light-years. It is also worth noting that this telescope will observe the area more than 400 times larger than the area viewed by Kepler. While the Kepler telescope looked further into space in a more narrow sector, the TESS space telescope will first and foremost explore the nearest section of space. However, its gaze will cover a sector hundreds of times wider. Among the first successes of TESS is mapping of more than 75% of the visible night sky and identifying more than 2,000 exoplanet candidates based on transmitted data. Most recently, in August of 2022, TESS discovered the unique planet TOI 1452b, which is 67% larger than Earth, according to scientists. At the same time, 22% of its surface is covered by water. Calculations suggest that it receives as much energy as our Venus receives from the Sun, which makes it the ideal candidate for further study. It is expected that TESS will discover over 20,000 transit exoplanets, 500 to 1,000 of which will be terrestrial and super-Earth planets. As for the latest devices that will continue the search for exoplanets in the future, we have to mention the recently launched James Webb Telescope, which already had incredible results. You can find a video on our channel that will tell you in detail about every aspect of its work, as well as all of its features. Now let's briefly talk about why the JWST is necessary when we already have a substitute for the Kepler in the form of TESS. Both the Kepler telescope and the TESS telescope, although they were and continue to be incredibly powerful tools for observing space and stars, they still face the same problem as all photographic-type telescopes. Just like the Hubble telescope, the telescopes in question have certain limitations in their search, primarily to do with the spectrum of light they're able to see. In contrast, the James Webb Telescope has eyes that can operate outside of the visible spectrum. It has the ability to see farther and in more detail, the ability to look deeper and deeper into the universe and its mysteries through the gas clouds. And now we should give it credit for its achievements in the search for exoplanets. The first was a detailed study of the two exoplanets WASP-96 and HIP-65426b. Detailed imaging of HIP-65426b showed things that were previously unknown about this planet, found in 2017. Its size, temperature, and approximate composition of the atmosphere. As for WASP-96, the telescope recorded the first clear evidence of the presence of carbon dioxide in the atmosphere of a planet outside the solar system. Further observations surprised scientists even more. Distinct traces of water were found, as well as evidence of clouds and haze in the atmosphere surrounding a hot gas giant planet orbiting a distant sun-like star. Right now, thousands of earthly telescopes and eyes of those craving knowledge about space are peering into the depths of space, as well as two brand new space telescopes, TESS and Webb. Although the science that studies exoplanets is relatively young, we're already seeing how man-made tools are pushing the boundaries of visible space further and further. Perhaps our new house can already be seen through their lenses. Have we finally found the answer to one of humanity's oldest questions? Are we alone in the universe? The James Webb Space Telescope may have just brought us one step closer to a revolutionary discovery. Meet K2-18b, a distant exoplanet that has suddenly found itself at the forefront of astrobiological research. Why? Because James Webb discovered something unusual in its atmosphere, something that could potentially signal the existence of life. Water vapor, methane, and even the rare dimethyl sulfide are not just random molecules. They may be the biosignatures we are looking for, clues that life in some form exists beyond Earth. Armed with the most advanced space technology ever created, James Webb is our new guardian of the galaxy, a telescope designed to peer into the unknown and perhaps redefine our understanding of life itself. So, are you ready to venture into the unknown and dive into the mysterious world of K2-18b? As we venture deeper into space in search of answers to questions that have puzzled humanity for generations, we rely on the eyes of our technological marvels to bring the universe into focus. One such eye is the James Webb Telescope, or JWST. For decades, the Hubble Space Telescope has been our window to the universe, producing images that have both delighted and enlightened us. But even Hubble has its limitations. Meet James Webb, a telescope dedicated to pushing the boundaries of what we can see and understand. One of the most innovative features of the JWST is its cool screen technology. This is no ordinary sunshade. It's a multi-layered engineering genius the size of a tennis court that blocks the heat of the sun, earth, and moon. Why is this important? Because it allows the telescope to cool to incredibly low temperatures, increasing its sensitivity to the faint infrared signals emitted by distant celestial bodies. Infrared observations are crucial for studying exoplanets such as K2-18b. Unlike visible light, which can be absorbed or scattered by space dust, infrared waves can overcome such obstacles, giving us clearer and more detailed images. JWST's ability to make infrared observations is not just an achievement, it is a revolution in the way we study distant worlds. So what discoveries await us when we turn his gaze to K2-18b? Located 124 light-years away in the constellation Leo, this exoplanet is more than just a distant rock. You may have heard of the Goldilocks Zone, a term describing the habitable zone around a star where conditions are ideal, neither too hot nor too cold, for liquid water to exist. K2-18b orbits around its parent star, K2-18, in just this zone. But what sets it apart from other exoplanets in similar orbits? K2-18b is not just another rocky planet. It is what scientists call a Hycean world. Hycean worlds characterized by a hydrogen-rich atmosphere and a surface covered by a watery ocean represent a new frontier in our search for extraterrestrial life. They offer conditions that may be similar to those around hydrothermal vents on Earth, which are known to support diverse ecosystems. Recent observations by the James Webb Space Telescope have revealed intriguing details about the atmosphere of K2-18b. From water vapor to methane and even potential traces of dimethyl sulfide, the atmosphere of this distant world is a cocktail of elements and compounds that could support life, or at least life as we don't yet know it. The discovery of these atmospheric components has caused a wave of excitement in the scientific community. Researchers are full of excitement and speculation as they ponder the implications of these discoveries for astrobiology and the broader quest to understand the nature of life in the universe. Could this Hycean world with its unique atmospheric composition be the key to unlocking the mysteries of extraterrestrial life? And what might its unique conditions mean for the future of astrobiology? When we venture into the field of exoplanet exploration, one of the most challenging but rewarding aspects is the study of alien atmospheres. K2-18b, with its unique location in the habitable zone and intriguing atmospheric composition, provides a compelling example. While Earth's atmosphere is a mixture of nitrogen, oxygen, and gas impurities, K2-18b is a very different cocktail. This exoplanet's hydrogen-dominated atmosphere, with traces of water vapor, methane, and perhaps even dimethyl sulfide, is a treasure trove of scientific curiosities. Studying the atmosphere of an exoplanet more than 100 light-years away is not an easy task. It involves a technique called spectroscopy, which analyzes the light from the planet's parent star as it passes through the planet's atmosphere. Different molecules absorb light of specific wavelengths, creating a unique fingerprint that can be deciphered to determine the composition of the atmosphere. The infrared capabilities of the James Webb Space Telescope played an important role in these discoveries. The Mid-Infrared Instrument Spectrograph, abbreviated MIRI, allows for an extended range of wavelengths, allowing it to detect a variety of molecules that were previously elusive. The presence of methane and the lack of ammonia in K2-18b's atmosphere has scientists speculating about the types of life that might exist there. On Earth, methane is often produced by biological processes, and its presence on K2-18b opens up the possibility of life forms that thrive in a hydrogen-rich environment, something we've never encountered before. The composition of K2-18b's atmosphere also suggests the presence of a subsurface ocean. This opens up exciting questions about atmosphere-ocean interactions and how these dynamics might affect the overall habitability of the planet. So could its atmosphere be the key to a new understanding of habitability and life beyond Earth? When we think of life, we often imagine Earth-like environments, but in fact life exists in environments where we can't even imagine. Studying extremophiles, organisms that thrive in extreme environments, opens up new possibilities for studying life beyond Earth. Deep in Earth's oceans, hydrothermal vents spew hot, mineral-rich water, creating an environment devoid of sunlight, but teeming with life. Extremophiles such as the thermophiles and acidophiles thrive there, challenging our traditional understanding of what life needs to survive. Could such life forms exist on exoplanets like K2-18b? The hydrogen-rich atmosphere of K2-18b offers unique conditions for previously unexplored life. On Earth, certain microbes called methanogens produce methane in an oxygen-free environment. If methane in the K2-18b atmosphere is produced biologically, we may be in a world where hydrogen-loving extremophiles thrive. The study of extremophiles expands the range of conditions in which life can exist. From the acidic rivers of Rio Tinto in Spain to the tundra of Siberia, life on Earth exists in a wide variety of extreme environments. This diversity encourages us to reconsider the ecological limits of extraterrestrial life. The potential for a subterranean ocean and hydrogen-rich atmosphere makes K2-18b an attractive target for studying extremophiles in the exoplanet environment. Perhaps this distant world has its version of extreme life, adapted to such conditions and considering them a name for itself. If extremophiles do exist on K2-18b, what might be their evolutionary trajectory? On Earth, life began with simple, single-celled organisms and evolved into complex forms. Could a similar process occur in other worlds given enough time and the right conditions? One of the most interesting aspects of studying the K2-18b atmosphere is the potential presence of dimethyl sulfide, or DMS. On Earth, this compound is often produced by marine phytoplankton and serves as a potential biosignature. But could its presence on an exoplanet like K2-18b also indicate life? In the Earth's oceans, DMS is produced by phytoplankton and serves many ecological functions. It is a compound that, when oxidized in the atmosphere, can lead to cloud formation. Its presence in exoplanet atmospheres, such as that of K2-18b, could be a game changer in the search for extraterrestrial life. The potential detection of DMS on K2-18b is still being tested. The James Webb Space Telescope's mid-infrared instrument spectrograph is capable of detecting such complex molecules, but confirming their presence requires careful analysis and expert judgment. The discovery of potential biosignatures such as DMS at K2-18b has excited the scientific community. However, like any groundbreaking discovery, it's also sparked a debate that oscillates between skepticism and optimism. The scientific community is divided on the implications of the discovery of DMS on K2-18b. While some consider it a strong candidate for biosignatures, others warn that abiotic processes can also produce similar compounds. The debate emphasizes the complexities and challenges in interpreting exoplanet data. Historically, astronomical discoveries have often been met with skepticism. When Galileo first discovered the satellites of Jupiter, his findings were initially rejected by many. Similarly, the discovery of the first exoplanet in 1995 was met with caution. These historical examples serve as a reminder that skepticism is an integral part of the scientific process. The search for extraterrestrial life doesn't depend on a single molecule or observation. Scientists are looking for a combination of biosignatures to create compelling evidence for the existence of life. Could DMS be a part of a larger puzzle involving other biosignatures like methane and water vapor? The debate's likely to continue until additional data is collected. As technology advances, future missions with even more sensitive instruments may provide the confirmation needed to classify the DMS as a true biosignature. Is DMS the key we have been waiting for in the search for alien life, or is it a distraction that is throwing us off track? Either way, the debate itself is a testament to the ever-evolving nature of scientific research. The James Webb Space Telescope has revolutionized our understanding of exoplanets like K2-18b, but it's just one step in a long journey of space exploration. What lies beyond this monumental mission, and how will future technologies continue to expand our cosmic horizons? The extremely large telescope, scheduled for completion by 2025, promises to be another game changer. With a main mirror diameter of 128 feet, it will be the largest near-infrared optical telescope in the world. Its unprecedented sensitivity could confirm or refute the biosignatures detected by the James Webb Space Telescope. The Large UV Optical IR Surveyor, or LUVOIR, is another mission on the horizon that could complement James Webb's findings. Designed to operate over a wide range of wavelengths, LUVOIR can provide even more detailed atmospheric analysis and potentially obtain direct images of exoplanets. As we target more distant exoplanets, advances in propulsion technology will be critical. Components like ion propulsion and even theoretical methods involving antimatter propulsion could drastically reduce travel times, allowing probes to reach and study exoplanets within a human lifetime. We've previously published a video on the possibility of interstellar travel and the challenges associated with it. As we stand on the threshold of potentially revolutionary discoveries, it's worth pausing to consider the philosophical implications and questions that fuel our cosmic curiosity. What does the search for extraterrestrial life mean for our understanding of existence, and what questions does it pose for the future? One question that's becoming relevant is the role of red dwarfs in the galaxy. Could these numerous stars, often overlooked because of their small size and dim light, actually be the cradle of life? Their longevity and stability make them intriguing candidates for planets that have life. What would the discovery of extraterrestrial phytoplankton mean for our understanding of life? Such a discovery would not only confirm the existence of life beyond Earth, but would also suggest that the building blocks of life are more universal than we thought. What will the next decade reveal in our quest to understand the cosmos? Will we confirm the existence of extraterrestrial life? Or will we discover new, even more complex questions that challenge our understanding of the universe? Have you ever wondered if black holes, those mysterious cosmic objects that consume everything in their path, might hold the key to understanding the most elusive force in the universe, dark energy? On the one hand, there's dark energy, which makes the universe expand with incredible acceleration. On the other hand, black holes create such a strong gravitational pull that not only planets and space objects, but even light itself cannot escape from its death grip. Even individually, these things sound like something unbelievable from the realm of science fiction. What if these two mysteries of the cosmos are connected? What if black holes, these cosmic eaters, are also cosmic creators, generating the force that is pushing the universe apart? This is an idea that scientists have been exploring in recent years, and quite recently, they've shown that this could be a very real possibility that could fundamentally change our understanding of the universe. To understand the connection between black holes and dark energy, we first need a clear definition of what dark energy is and why it's so mysterious in modern astrophysics. Dark energy is a hypothetical form that permeates all of space and causes the universe to expand with acceleration. It was first proposed in the late 1990s when astronomers studying distant supernovae noticed that they were moving away from us much faster than expected. This discovery led to the realization that the expansion of the universe is not slowing down, as one would expect due to the gravitational pull of all matter in the universe, but is in fact accelerating. This suggests that there's some invisible force pushing the galaxies apart at an ever-increasing rate. Dark energy is one of the most fundamental mysteries of modern astrophysics, and there are several reasons for this. First, we don't know what it's made of or how it works. It is unlike any form of energy or matter that we know of, and it doesn't seem to interact with anything else in the universe except through gravity. Second, dark energy makes up a staggering 68% of the total energy density of the universe. But we can't directly observe or measure it. Instead, we infer its existence based on its effect on the expansion of the universe and the cosmic microwave background radiation. Finally, there are several competing theories explaining the origin and nature of dark energy, none of which have yet to be conclusively proven. Some scientists suggest that dark energy is simply a cosmological constant, a fixed density of energy inherent in the structure of space-time. Others suggest that it may be a form of exotic matter or a scalar field that changes with time. Over the past few decades, scientists have worked hard to unravel the mysteries of dark energy, and the field is still in its infancy. We don't know much, but one thing is clear. Dark energy is one of many intriguing and important phenomena in the universe. Now, to understand how black holes can be related to dark energy, we need to look more closely at their formation, properties, and role in shaping the large-scale structure of the universe. A black hole is a region of space where the gravitational pull is so strong that nothing, not even light, can escape its grip. They are formed when massive stars collapse under the action of their own gravity at the end of their lives, leaving behind a small but incredibly dense point in space. Despite their strange nature, black holes play a crucial role in shaping the large-scale structure of the universe. They are thought to be responsible for the formation of galaxies because their enormous gravity can attract and pull together large amounts of matter. When matter collapses into a black hole, it releases enormous amounts of energy, which can create radiations and jets of plasma that repel the surrounding matter, much like a cosmic water tornado. This powerful outflow has the potential to accelerate the expansion of the universe, making black holes an even more important player in the cosmic landscape. The assumption of a potential connection between black holes and dark energy is closely related to the mystery surrounding the expansion of the universe. Although dark energy has been a significant breakthrough in our understanding of the universe, it has also complicated the task of observing the theoretical field of cosmology. To explore the theoretical foundations of dark energy, we must carefully examine the standard model of cosmology and the problems of the cosmological constant, including the expansion of the universe. The standard cosmological model is the prevailing model of the evolution and structure of the universe. It is based on the idea that the universe began with a Big Bang, which created all the matter and energy in the universe. Over time, the universe expanded and cooled, leading to the formation of galaxies and other large structures. However, the standard model of cosmology also predicts that the expansion of the universe should slow down over time. This is because gravity, according to the theory, should pull matter together and slow down expansion. However, in the late 1990s, astronomers discovered that the expansion of the universe was actually accelerating, which was completely unexpected. This discovery led to the assumption of dark energy, a mysterious force that accelerates the expansion of the universe. The simplest explanation for dark energy is the cosmological constant, a term of Einstein's general theory of relativity that describes the constant density of energy throughout space. However, the cosmological constant poses a serious problem for cosmologists. The observed acceleration of the expansion of the universe far exceeds that predicted by the cosmological constant, and it is not clear why the energy density of the universe must be so finely tuned to produce this effect. To solve this problem, cosmologists have proposed a number of alternative theories of dark energy. One possibility is that the cosmological constant is not actually constant, but may change with time or depending on the condition of the universe. Another possibility is that dark energy is caused by some other form of energy, such as a new field or particle, which has not yet been discovered. While there's no consensus on the exact nature of dark energy, one thing is clear. It poses a serious problem for our current understanding of the universe. To fully understand the meaning of dark energy, we'll need to further explore the theoretical foundations of cosmology and develop new models and theories to explain this mysterious force. So how can black holes be related to this phenomenon? To answer this question, we need to study the mechanisms by which black holes generate energy. Black holes form when massive stars collapse under their own gravity, creating an object with such a strong gravitational pull that nothing, not even light, can escape its grasp. When matter falls into a black hole, it forms an accretion disk, a rotating disk of superheated gas orbiting the black hole. One of the ways black holes can generate dark energy is through their accretion disk. At its core, this idea is based on the fact that black holes are incredibly efficient at converting matter into energy. This accretion disk is a source of enormous energy, as the gas is heated to incredibly high temperatures by the friction generated as it moves around the black hole. Part of this energy is emitted in the form of radiation, including X-rays and gamma rays, But the most interesting aspect of an accretion disk is that it can create negative pressure, which is a force acting against gravity. This force pushes matter away from the black hole. This negative pressure is the key to the connection between black holes and dark energy. It turns out that negative pressure is a characteristic of dark energy, which is considered a type of energy that permeates all space and has negative pressure. The idea is that the negative pressure created by an accretion disk around a black hole may contribute to the overall negative pressure of dark energy in the universe, causing it to accelerate the expansion of the universe. Another mechanism by which black holes can generate dark energy is Hawking radiation. This is a process in which black holes emit particles, including photons and other subatomic particles, due to quantum mechanical effects on the event horizon. These particles take energy away from the black hole, causing it to lose mass and shrink over time. This process may also contribute to the negative pressure of dark energy in the universe, since the energy emitted by black holes is believed to be related to the total energy density in the universe and contribute to the acceleration of its expansion. A recent study published in the Astrophysical Journal Letters provided observational evidence that black holes are related to the power of dark energy. The study was based on observations of the motion of galaxies, in particular their peculiar velocities. In astronomy, peculiar velocity refers to the velocity of an object relative to a certain reference point, such as the average motion of galaxies in a certain region. It differs from the total velocity of an object, which accounts for the expansion of the universe. Unusual velocities can be caused by gravitational attraction or repulsion between objects, and their study can provide information about the distribution of matter in the universe. To measure the peculiar velocities of galaxies, they used a technique called the redshift space distortion method. The team used data from the Sloan Digital Sky Survey, SDSS, including the largest collection of galaxy distances and velocities. The results showed that the peculiar velocities of galaxies correlate with the local density of matter, including dark matter, as well as with the density of black holes. This suggests that the motion of galaxies is affected not only by the gravity of the visible matter, but also by the presence of black holes. If this correlation is confirmed by further research, it could support the idea that black holes contribute to accelerating the expansion of the universe, possibly serving as a source of dark energy. Another piece of evidence comes from the observation of supermassive black holes. These are black holes that are millions or even billions of times more massive than our Sun and are thought to be present in the centers of most galaxies. When matter falls into these black holes, it generates enormous amounts of energy, including radiation that can be detected with telescopes. Recent studies have shown that the radiation from these supermassive black holes may contribute to the total energy density of the universe and may even be a source of dark energy. Although this idea is still being investigated, it provides another intriguing link between black holes and the mysterious force that drives the expansion of the universe. Finally, measurements of the cosmic microwave background provide another piece of evidence supporting the idea of black holes as a source of dark energy. This is the afterglow of the Big Bang, and it provides a snapshot of the universe as it was shortly after its formation. Recent studies have shown that fluctuations in the cosmic microwave background may be related to the presence of black holes in the early universe, and that these black holes may have contributed to the total energy density of the universe. Overall, although the connection between black holes and dark energy is still the subject of ongoing research, there's some evidence that this connection may be valid. As astronomers continue to investigate the properties of black holes and the nature of dark energy, we can better understand the role that black holes play in shaping the evolution of the universe. Although the idea of black holes as a source of dark energy is fascinating, it is important to consider alternative explanations and criticisms of the theory. One alternative explanation for dark energy is the possibility of the existence of a new fundamental particle or field, which has been proposed in some theories. This particle or field would have a negative pressure similar to the cosmological constant and could explain the observed acceleration of the expansion of the universe. Another alternative is the theory of modified gravity, which suggests that our current understanding of gravity is incomplete and in need of revision. This theory proposes modifications to Einstein's general theory of relativity that could explain the observed acceleration without the need for dark energy. There's also several problems associated with detecting and measuring the effects of black holes on dark energy. One problem is that black holes are difficult to observe directly because they do not emit any light. Instead, astronomers must rely on indirect observation, like gravitational lensing of background stars and galaxies. Another problem is to distinguish the effects of black holes from other astrophysical phenomena that may also affect the expansion of the universe. For example, the distribution of matter in the universe can cause changes in the observed rate of expansion, which can be mistaken for the effects of dark energy generated by black holes. And finally, as with any scientific theory, further research and testing are needed to confirm or disprove the idea that black holes are a source of dark energy. This could include the use of new telescopes and observatories, such as the James Webb Space Telescope or the upcoming Large Synoptic Survey Telescope, to look for evidence of black holes and their influence on the expansion of the universe. It's also clear that we will need further theoretical work to refine our understanding of the physics of black holes and the nature of dark energy. As we continue to push the boundaries of our understanding of the universe, the possibility that black holes might be the key to unlocking the mystery of dark energy is a tempting prospect. Imagine the consequences of such a discovery. Not only will it shed light on the elusive force that dominates the cosmos, but it would revolutionize our understanding of the universe and our place in it. Instead of being mere cosmic disruptors, black holes will also be responsible for the expansion of the universe itself. This will require us to reconsider our views on fundamental physics and the nature of space-time, and may lead to new discoveries and breakthroughs in astrophysics and cosmology. This vision inspires scientists around the world to continue pushing the boundaries of knowledge, and it captures the imagination of all who dare to dream about the mysteries of the universe. Let us continue to explore this exciting frontier of science, and who knows what we may discover in the coming years. For our universe has been and will continue to be full of mystery and mystery. Like clockwork, every 22 minutes for the past 35 years, a signal has pierced the silence of space and reached Earth. It's not a satellite or any man-made object. It's a signal from deep space, which is a mystery. Scientists call it GPM J1839-10, but its origin remains mysterious. Is it a message, a phenomenon, or a clue to something bigger? This signal, captured by one of Earth's most powerful telescopes, has become the subject of global curiosity and debate. Where could it be coming from, and why should we care? Today we'll delve into a cosmic detective story that challenges our understanding of the universe itself. Let's get started. So how can we tune in to unlock the secrets of such a signal? The tool that makes our space exploration possible is radio astronomy. The story begins in the 1930s when American physicist Carl Jansky was researching radio interference. What he discovered was unexpected: radio waves emanating from the Milky Way. This accidental discovery marked the beginning of radio astronomy. Unlike traditional astronomy, which relies on visible light, radio astronomy listens to the universe. It tunes to frequencies inaccessible to the human eye, revealing celestial phenomena that would otherwise remain hidden. Since its inception, radio astronomy has undergone a technological revolution. Today's radio telescopes are marvels of engineering, capable of picking up signals from unfathomable distances. In the remote outback of Western Australia sits a space detective unlike any other, the Murchison Broadband Array. It's not just a telescope, it's a sophisticated network designed to explore the farthest reaches of the universe. Composed of thousands of antennas scattered across an arid landscape, the Murchison Widefield Array is an engineering feat and a testament to human curiosity. Each antenna is like a finely tuned ear listening intently to a whisper. Behind the scenes, a team of dedicated scientists and engineers work tirelessly to calibrate and maintain this complex system. What's their goal? To pick up signals over a wide range of frequencies. This is crucial for studying different celestial phenomena, as each emits its own unique radio signature. Once captured, these signals are processed in a state-of-the-art data center. Here, powerful algorithms sift through the cosmic noise to identify patterns and anomalies, turning raw data into valuable scientific discoveries. Among the array's most intriguing catches are fast radio bursts, or FRB. These high-energy phenomena are incredibly brief, lasting only milliseconds, yet emit as much energy as the sun emits in nearly a century. It was in this cosmic cacophony that our mysterious GPM J1839-10 signal was discovered. Unlike other signals, this one has a rhythmic pattern and has been arriving at Earth every 22 minutes for the past 35 years. What sets this signal apart is its consistency and longevity. While most cosmic signals are random or short-lived, this one's proven to be both stable and constant, making it a subject of intense study and debate. So unlike time signals that come and go, GPM J1839-10 arrive continuously every 22 minutes without fail. Its rhythmic pattern is unlike anything we've encountered in the field of radio astronomy. For 35 years, it's maintained this cycle, challenging our understanding of cosmic phenomena. The initial discovery was met with skepticism. Could it be an artifact or some kind of interference? Rigorous checks were made, and yet the signal persisted. Subsequent observations only confirmed its existence, making it one of the most enduring mysteries of radio astronomy. So what makes GPM J1839-10 different from other cosmic signals? Most signals from celestial bodies such as pulsars and magnetars are either sporadic or have different intervals, but not this one. Its 22-minute periodicity is like a metronome in a vast orchestra of cosmic signals, a rhythmic constant in a sea of variables. Further analysis reveals even more peculiarities. The waveform does not follow the typical profiles of known celestial radio emissions. Its frequency and amplitude have nuances that have yet to be fully understood, complicating an already confusing mystery. Many theories have been proposed, from rotating neutron stars to strongly magnetic magnetars, as well as even more exotic theories like the interaction between double black holes. However, none of them meet all the requirements perfectly, and that leaves the scientific community in a state of intrigued bewilderment. When it comes to mysterious radio signals from space, suspicion often falls on pulsars. These celestial beacons are known to emit beams of radio waves, making them prime candidates for any unexplained cosmic chatter. But what are pulsars? Pulsars are neutron stars born from the remnants of massive stars that have become supernovae. They spin at incredible speeds. When they spin, their magnetic fields generate beams of electromagnetic radiation, including radio waves. These rays sweep through space like the beams of a lighthouse on the sea. When these rays cross the Earth, our radio telescopes pick them up as pulses, hence the name pulsars. The signals from pulsars are usually quite regular, often with millisecond accuracy. This predictability has even led to the use of some pulsars as space clocks to aid in tasks such as spacecraft navigation. So, could GPM J1839-10 be a pulsar? At first glance, one might think so, given its rhythmic 22-minute interval. However, if you dig deeper, the differences become obvious. Unlike typical pulsar signals, which have a constant shape and amplitude, GPM J1839-10 exhibits features that set it apart from others. Its waveform does not follow the profiles we usually associate with pulsars, and its amplitude exhibits variations that have yet to be explained. Moreover, the longevity and permanence of the signal contradict what we know about pulsars. These celestial objects can slow down over time due to a loss of rotational energy, which would affect the timing of the signals they emit. Nevertheless, GPM J1839-10 has remained unchanged for more than 3 decades. To summarize, although pulsars are often the culprit behind mysterious radio signals, this time they seem to have been left innocent. While pulsars are often the first names on the list when it comes to cosmic radio signals, magnetars round out that very list. Magnetars are neutron stars that don't quite fit the pattern, with magnetic fields so strong they defy comprehension. To understand the magnitude of a magnetar's magnetic field, consider this. It is about 2 quadrillion times stronger than Earth's magnetic field and 20 trillion times more powerful than a refrigerator magnet. These are magnetic fields so strong they can erase data from a credit card halfway to the sun. Magnetars are known for their bizarre properties. They emit X-rays and gamma rays, but can also produce radio emissions. These emissions are often associated with stellar earthquakes, seismic events on the surface of a magnetar that release enormous amounts of energy. Imagine an earthquake, but on a cosmic scale. These stellar earthquakes can distort the magnetic field of the magnetar, causing the release of energy in the form of electromagnetic radiation, including radio waves. So, could a magnetar be the source of our mysterious GPM J1839-10 signal? Well, at first glance, it might seem plausible. After all, magnetars are known for their strange behavior. However, the concept of starburst fails to explain the constant 22-minute signal interval and its longevity. Starbursts are sporadic events, and their emissions will not have this rhythmic, clock-like precision of GPM J1839-10. Moreover, starbursts tend to change the magnetar's rotation period and magnetic field with time, which is not consistent with the unwavering consistency of our enigmatic signal. Despite their bizarre and extreme properties, magnetars are not the key to solving the mystery of GPM J1839-10. While they offer an intriguing possibility, the evidence, or lack thereof, takes us back to the drawing board in search of a better explanation. As we continue to explore astrophysics theories regarding GPM J1839-10, we come up with hypotheses that, while less common, offer tantalizing possibilities for the source of this enigmatic signal. First on the list is the white dwarf hypothesis. White dwarfs are the remnants of stars that have exhausted their nuclear fuel. They're incredibly dense and have strong magnetic fields and can theoretically cause radio emissions. Could a white dwarf be the signal emitter behind GPM J1839-10? Again, while the theory is intriguing, it faces problems. White dwarfs do not typically emit radio waves with the same level of consistency and periodicity as our enigmatic signal. Moreover, their magnetic fields, although strong, do not exactly match the features observed in GPM J1839-10. Another frontier theory leads us to the dynamic interactions between stars and exoplanets orbiting them. In this cosmic dance, the magnetic fields of the star and exoplanets can interact in ways that do produce unique radio emissions. While this theory offers a fascinating avenue of investigation, it also comes with its own challenges. Such interactions will likely produce a wide range of signals rather than the unwavering 22-minute cycle we observe with GPM J1839-10. Now finally, let's look at double brown dwarfs, objects on the boundary between planets and stars. When two such brown dwarfs orbit around each other, their magnetic fields can interact, potentially emitting radio waves. Now again, while this theory breaks new ground, it's not fully consistent with the data we have. Magnetic interactions between double brown dwarfs are likely to produce a more chaotic signal rather than this rhythmic, clock-like pulse of GPM J1839-10. As we continue to unravel the mystery of GPM J1839-10, a new perspective is emerging that takes into account the environment in which the signal exists. Could surrounding cosmic debris and stellar winds influence the signal patterns we observe? Imagine a radio signal traveling through space and encountering asteroids, gas clouds, and streams of charged particles along the way. These environmental factors can act as space filters, changing the characteristics of the signal by the time it reaches Earth. The idea is not purely speculative. Studies have shown that space debris can indeed affect the properties of radio signals, causing changes in amplitude and even frequency. But is this a case with GPM J1839-10? Stellar winds, streams of charged particles emitted by stars, that's another environmental factor to consider. These winds can interact with the radio signal, causing it to oscillate in ways that may explain some features of GPM J1839-10. Interestingly, the results of fast radio burst 201-809-16b offer some parallels. This particular FRB exhibited patterns that were puzzling at first, but were later found to be influenced by the local environment, including the presence of a nearby magnetar and the surrounding cosmic plasma. Could a similar environmental influence occur with GPM J1839-10? Although the contexts are different, the idea that local space conditions can affect the radio signal adds another layer of complexity to our understanding. As we approach the final frontier of this study, it's time to consider the broader implications of this enigmatic signal and what the future holds for its study. Fortunately, the source of GPM J1839-10 remains active, its signal still traveling through the vast cosmos to reach us here on Earth. This opens the door for anyone around the world with the right tools to observe it, adding their own notes to this cosmic symphony of discovery. Dr. N. Hurley Walker, standing at the helm of previous research, and her colleagues are already on the case, planning to continue their observations as well as examine archival images in search of similar phenomena in the Milky Way. Their ongoing efforts are aimed at solving this mystery, and their initial results are promising. The discovery of GPM J1839-10 has confirmed that ultra-long period radio sources are not as rare as previously thought. This suggests that upcoming studies in the galactic plane may reveal even more examples, expanding our understanding of these enigmatic signals.